Okay, so hello students. Let us start with BVLSI lecture number 44. Today is 13th April. So I'll briefly revise what we have done in the last two lectures for the CMOS inverter, and then I'll proceed for the today's topic. Alright. So we have completed resistive load NMOS inverter, and we are starting with the CMOS inverter. In CMOS inverter, first we have seen its circuit diagram, the structure of it. So it consists of a PMOS load and NMOS driver with both its gate terminal connected together, and this is applied to the input. Here we have the supply voltage VDD, and here we have the ground, and here is my output measured with respect to ground. Okay, so this is my CMOS inverter circuit, and we have seen its VTC curve in briefly. Last time also we have derived this. So it's a graph of V in versus V out. It is voltage transfer characteristics curve. Okay, and ideally how this curve should be, ideally this curve should be like this. For lower inputs, output should be equal to VDD, and for higher inputs the output should be equal to 0. So there are these two states. So this is my ideal VTC curve. Okay, practically however differs from ideal, and we have a situation which is looking like this. Okay, so this is a practical VTC curve which we get from the CMOS inverter. Now we have identified certain regions A, B, C, D. This point is called as VTH or VDD by 2. Okay, similarly over here we have VDD by 2. Alright, here if we call this as VTN, the threshold voltage of NMOS inverter, then we have a region over here. Okay, like this. Now there is one more region which is over here, which is called as, this is VDD of course, this is VDD plus VTOP. Remember VTOP voltage is negative, so let's say VTOP voltage is -1, so VDD is 5, let's say. So this point will be at 4 volt. I hope you're understanding. Then let's say VTN is 1 volt, so this is 1 volt, this is 2.5, this is 4, and this is 5. Alright, so we get another region of operation over here, this one. Okay, and there is a small transition region over here in the middle where all the output is switching drastically from higher logic to a lower logic immediately. Okay, so these regions are defined as region number A here, this is A, B, this is C, this and between these two blocks, this is region number C, then D, and this is E. If I mark it over here till VDD, VDD plus VTOP till VDD, this is region E. And we have seen the during the last lecture in which mode of operation the NMOS and PMOS work in these different regions. So let us just revise. So in region number A, my NMOS is in cutoff, so you can write it down. Your PMOS is in linear region. In region number B, my NMOS goes to saturation, it turns on but goes to saturation. My PMOS remains in the linear region of operation. Region C, both NMOS and PMOS are in saturation, so they both are in saturation mode of operation. Region D, my NMOS is in linear mode of operation now, and my PMOS goes to saturation. Region number E, PMOS is off cutoff, and NMOS goes into remains in the linear region. So these are the different regions of operation, and it's divided into five intervals: A, B, region A, B, C, D, E. Okay, so from here on we'll continue further for the circuit analysis. Now, actually, this is CMOS inverter, so we have a capacitive load like this. So this is my capacitor. So during the whenever the input is 1, the capacitor discharges via NMOS transistor, and whenever the input is 0, the NMOS PMOS is on and the capacitor charges towards VDD. So you can see the direction of the current. So this current is called as IDP, drain current for PMOS transistor, and this is IDN. So ideally for all time we can say under static conditions IDN is equal to minus of IDP, but normally in all the textbooks they write it as this, as almost same as the drain current flowing to the NMOS is equal to the magnitude of drain current flowing to the PMOS. So this is true for all the operations. Okay, now also VGSN, N stands for NMOS transistor. So VGS voltage for NMOS transistor is just equal to V in. We have seen this. VDSN, this is equal to V out. Also, these are the constraints. These are called as the constraints. Then VGSP, for PMOS transistor it is V in minus VDD. We have also seen this. And VDSP is V out minus VDD. So these are the 5 constraints which we have to work around with. Alright, now further we will analyze and see now if we treat the same CMOS transistor separately. In the sense, let me just draw the same diagram over here. So let's say if I bifurcate my CMOS transistor as follows. So this is my PMOS transistor. Okay, this is my VDD. So here is my output, right? It is output. Here is my input. So I hope you know the terminals. This is source, gate, and drain terminal. Okay, and this is my PMOS transistor. The current is flowing into it. So this is IDP. Okay, this is my V out. And below I have my NMOS transistor. Of course, this is connected to the output. It's the drain terminal. This is going to the input, and the source terminal goes to the ground. Okay, and here the current flows in this direction. Let me mark the terminals: drain, gate, source, and the current is flowing down. IDN, drain current for the NMOS transistor. Alright, now what we do over here is, let me just write in step form. We will sweep the V out with V in as a parameter. We'll sweep V out with V in as a parameter. So we will be plotting actually the graph of IDP versus VDS versus IDS. Basically we'll plot the output characteristics. Okay, so let's say we are devoting V in as 5 parameters. So we are sweeping V out with a V in as a parameter. So V in equal to V1, V2, V3, V4, V5. Now why does 5 points? These 5 points are because of these precisely 5 regions. So maybe they are associated with region A, B, C, D, E correspondingly. Okay, so this is associated with, let's say V1 is associated with less than VTN, V5 is associated with greater than, this is a V in parameter. Now V in is less than VTON, so this is one region. V5 is V in greater than VDD plus VTOP. Okay, so similarly here in V3 we have region C where both the transistors are on. Alright, so both NMOS and PMOS are in saturation. So here we can say both are in saturation, both NMOS and PMOS. Remaining V2 and V4 we will see as we move around. Okay, fine. So let's sweep V out with V in as a parameter and plot the characteristics of which characteristics will plot. We'll plot the characteristics of VDS versus ID. Okay, for both PMOS and NMOS transistors. So that will make the CMOS transistor. Alright, so let's plot them together now. So here I will take so you all can also draw it together. This is VDS, this is ID. We can say IDN for the NMOS transistor. So this is VDSN. So what is VDSN basically? Can you tell me? It's V out, right? For the NMOS transistor. See, we have written the constraint now. I hope I am audible. Just confirmation from someone. Hello? Okay, okay. So VDSN is basically V out for the NMOS transistor and we have IDN. So we have to plot this characteristics for various values of V in. Okay. So for V1, where will the graph come for V in equal to V1? So for V in equal to V1, V in is less than VTON and V in is nothing but VGSN. Okay, so if VGSN is less than VTON, my transistor will be off. So where will my graph come? Where this will curve come? So I'll plot 5 curves. Let me start with this. So it will come on the x-axis. First curve. Let me mark this as this is your VDD. So first curve will come on the x-axis. This one. So what is this point? This point is V in equal to V1. Okay. So this is my VDD. This is VDD. This point is VDD. Okay. And this point is, this is the graph for V in equal to 0. Okay. The current is 0, right? Because the NMOS transistor is off. But what about the output? What about the output? Can you tell me? V in is 0. This is 0. Okay. But what about the output? Can you tell me what is VDS and V out? Here we can say V out is equal to VDD, right? See? V out is equal to VDD. If V in is 0, that is what this inverter means. Okay. Now, this V in equal to V1. Now we increase the value of V1. See, these are increasing values of V in, right? So this is V1. This is, let's say, V2, V3, V4, V5. So we are increasing the values of V1. Now we increase the value of V1, V in to V2. So how will be the graph? Let me draw it. So the graph will look something like this. Yeah. So this is the graph for V in equal to V2. Okay. Then next, we have a graph for V in equal to V3. So we get a higher value of current. Yes, of course. So V in is nothing but VGSN. So as we go on increasing the VGSN, the channel becomes more and more conductive. So V in equal to V3. We get this graph. Alright. And this is also the point where your V out is equal to VDD by 2. See, V in equal to V3 is when both the transistors are in saturation, and we have a point which is VDD by 2. Here also we have VDD by 2. Okay, and both the transistors are in saturation. So this point is called as threshold voltage of the inverter or the switching threshold of the inverter. Okay, anyways, we'll go further and we'll plot now next. Let me use brown color. V in equal to V4. So this is V in equal to V4. So as we go on increasing V in, that is VGS value, channel is becoming more and more conductive. Okay, and finally we will plot at the end V in equal to VDD or V in equal to V5. Okay, this is V in equal to V5, where V5 is almost like here, this point. V in is greater than VDD plus VTOP. Okay, so it's very close to VDD now at over here. So these are increasing values of V in. Okay, for PMOS transistor. So these characteristics I have drawn for my PMOS transistor. Are you getting the point? Yes or no? So let us plot, let us see now what happens. So let's say your V1 is over here. So if V1 is over here, V in equal to V1 is over here, my output is VDD almost. Okay, now we have come to V2. So V2 is somewhere around here, okay, in the region number B. So V out is slightly below VDD, but is almost equal to, you know, near the value of VDD, right? So here we can write here V out is approximately equal to VDD. Less than that, but approximately equal to. Then at V3 it's VDD by 2. What about V4? Let's search for the V4 point. So V4 point is somewhere around in region number D. So region number D, the V out has fallen to very low value in region number D. So somewhere around here we have V4, V in equal to V4, where output is just above 0. So we can say V out is at V4, V out is just greater than 0, about 0. And at V5, V5 is the point over here, the V out is equal to 0 over here. Okay, simply. I hope you are following this. Here we have V out exactly equal to 0. So for V in almost equal to VDD, your V out is equal to 0. So what is this characteristics? This is a graph of NMOS IDN versus VDSN graph. Okay, the current in the NMOS transistor versus the drain to source voltage in the NMOS transistor, which is nothing but V out. Alright, understood? Now similarly for PMOS transistor also we will draw. Okay, so for PMOS transistor, in which quadrant the graph will come? Can you tell me? For which quadrant the graph will come? This is first quadrant which we have drawn. Whether it will come in second, third, fourth quadrant, tell me. Anyone? Which quadrant the graph will come? This is 0. It will come over here, because over there the voltages are negative and the current is also negative. And what about this point? This point we call it as VGSP. Now can you tell me what is VGSP? VGSP? VGSP is V out minus VGSP is V in minus VDD. VGSP is V in minus VDD. Okay, so the graph will almost be reversed, and this will be IDP. Okay, so here now tell me what will be the first graph. Where will be V in equal to 0? Where will be V in equal to V1? Will it come on the x-axis or will it come at a maximum curve? Hello? Where will I plot V in equal to V1? See, V in equal to V1 means V1 is almost 0. Okay, so where it will come? V5, the V5, V in equal to V5 will come over here on the x-axis. Why? Because at V in equal to V5, V in is almost equal to VDD. So when V in is equal to VDD, what is VGSP? VGSP is almost equal to on the x-axis. Yes or no? Hello? You understanding? So this point, I'll use the same colors. So this point, this time, it will come on the x-axis. Let's say this is VDD. This point is VDD. So correspondingly, this graph will come over here. This is which point? V in equal to V5. This is the graph for V in equal to V5, because here V in almost equal to V5, which is almost equal to VDD, and if you substitute V in equal to VDD, you will get 0 over here, almost. Okay, so that's why it's you're getting at 0 x-axis, and then it will reverse. Okay, so whatever you got at V4, you will get first over here. So because it is V in minus VDD, so next graph will be over here. So this is V in equal to V4. I hope you are following. Then this will come V in equal to V3, where V out is equal to VDD by 2. Then your green curve will come. Sorry. V in equal to V4 curve will come here. Sorry, V2. Here it is V5. So V3, this is V2. Okay, and finally, what was on the x-axis there? It is the maximum current here. So this is V in equal to V1. Okay, so V in equal to V1. Here it is. Alright, are you understanding? Remember, for the PMOS transistor, the current is negative, and the VGS voltage is also negative. So this is different values of V in, right? And what is plotted on the x-axis? Basically VDSP. And what is VDSP given by? V out minus VDD. So remember it. Okay, where VGSP is what? V in minus VDD. VDSP is what? V out minus VDD. So that's why the graphs are coming like that. So if you want to relate it here, where V in is equal to V5, what is my V out? Equal to 0. Okay, so here this is VDD. So that's why the graph is looking like this. This is for the PMOS curve characteristics. Now what I have to do is I have to equate them. I have to equate IDSN is equal to minus of IDP. So what I will do over here is, whatever I've drawn over here, I'll mirror image it. Mirror image it on this side, over here on the left hand side, on the fourth quadrant. Okay, so let's do that. So I'll again take mirror image, means here V5 will come. Yeah, V5 will remain as it is over here. Then V4 will come over here like this. This is V4. Are you understanding why we are doing that? Because we are now saying ID and P is equal to minus of IDP. So this is IDP curve. This is the curve for IDP. Okay, and now we are drawing minus IDP. So minus IDP will come over here on the this side. So that's why we are drawing over here now. So this point will be V in equal to V4. This point is V in equal to V5. It will come on the x-axis only. Then next will be here. Sorry, let me draw it properly. Yeah, this is V in equal to V3, then V in equal to V2 curve will come, V in equal to V2, and finally V in equal to V1. Alright, yes or no? So this is the graph which we get. So don't get confused. This graph which we have drawn over here, this is minus IDP. Now we have to plot it together on one graph only, right? Now we have to plot IDS, ID. I mean both the. We are now saying that both the currents are same. IDS, IDN is equal to minus of IDP. So now what we will do? If you want to plot both of them together, if you want to plot both the currents together, so if I want to plot both the currents together, I have to make this positive, right? IDP. So what I will do now? Tell me. I'll superimpose this and mirror image this on the right hand side. So same graph, I'll draw it on the right hand side. Mirror image on the right hand side. So that will give me the proper values. Okay. So let me transfer this graphs here. I'll transfer the entire graphs on the left hand side to the right hand side. Now let's see what I'm doing carefully. So I'll use the same color code. So first is the orange curve. The orange curve, we will have the maximum point over here like this. Here, this is my point. This is my orange curve. Let me draw it properly. Here, this is where it will come. This, yeah, this one. This is orange curve, and then the green one. Sorry for that. The green one. Okay, let me draw it properly. Okay, then the blue one. Okay, and finally the green one. Alright, sorry, not over here. The green one will be, this is let me draw this again. This is the green one. Okay, this all they will meet at VDD. They'll start from VDD. Then the blue will come. Then again the green. No, blue has gone. Now the brown. Okay, and finally on the x-axis we will have the pink one. So they'll coincide. See, orange and x, orange and light pink. So there are 5 operating points. So whichever color matches. So one point is over here. Do you see this one point? One is over here. Pink matches with pink. Here, this one. Then we have this point over here. This point of intersection over here. Where this, don't get confused with the colors. This one, the brown one, and this brown one, we have one point over here. Then we have blue. For blue, we have somewhere around here. See this point. Then green and green matches over here. So this is the point. Then orange and orange matches over here in VDD. So this is the orange point. So these are the 5 point of operation. So this is the one. So this is region number C. This region number C, the point C. This one. Remaining points have no other significance. Only these 5 points which I marked have significance. This is region number C. Okay. Where is my region number A? Can you tell me? Region A, where it is which color point? Where output is VDD and input is almost 0. Which point it corresponds to? Yeah, this one, orange one. This is A, region A. B, region B is the green one, where the two green curves intersect. So this is region number B. This is brown one, region E. And here, this light pink is my region. Sorry, this is D. Brown one is D. And this is E. Okay, at region E, your V out is 0, but V in is maximum, as you can see. Okay, so at these points, these operating points only, we have this 5 regions which I've defined over here. So these points come from there. Alright, so this is the graph of ID and the drain current for both the NMOS and PMOS together, along with my output and input curves, where input is the parameter. I don't know how much you have followed from here, but this is what the reality is when we intersect both of them together, because we are combining both NMOS and PMOS together, right? So obviously the current should match up at some point of level, and when they match up, this is how the graphs look like. So can you tell me where is the maximum current obtained in which region of operation? A, B, C, D, E. Maximum current is obtained in which region of operation? Can you tell me from the graph? Hello? Okay, see the points and tell me, no? Where you get maximum current. Yes, in region C. So it's correct also, because both the NMOS and PMOS are in saturation over here. So both NMOS and PMOS are in saturation. So maximum current in the device flows in region C. Okay. Alright. In region number A, almost no current flows, but the output is V out. And region number E, almost no current flows, but the output is 0. Here it is. Okay. Yes. Alright. So this is what the consequences of joining both the currents together. So now we'll define the threshold voltage for the inverter. Okay, so now analysis come. Now this was the explanation part. I hope it is clear now. So from this, what do we learn? We have justified the superimposed the both the currents together, and we have seen the point of overlap. I've used the color code over here for point of overlap. These are the operating regions. Okay, and we have seen that in region number C we get the maximum current. In region A and E there is hardly any current flowing. In region number D and B there is current flowing, but we have to still determine how much. It's less than region number C. Okay, and but maximum current flows in region number C, that is for sure, and almost no current flows in region number E and A, that is also for sure. Alright, now we have to define the threshold voltage for the CMOS inverter. Can we start with this? Now the analysis will start. So please, everything what I am writing over here now, you can also note it down. Okay, let me connect my writing pad once more time. Yeah, so yeah, let's write down. Let me just reduce the thickness of my pen. Threshold voltage or switching threshold of CMOS inverter. Okay, this is also called as, the switching threshold is also called as trip point. Alright, Now if I want to calculate the switching threshold for an ideal VTC curve, how will it be? This is V in, this is V out, and if I want to find ideally the graph will look like this, right? And practically the graph will be like this. Okay, so if we plot a line passing to the origin, that is V in equal to V out, this line is V out equal to V in with a slope of 1. Okay, and this where this green curve intersects the VTC curve, that is my switching threshold. So this point is called as my switching threshold. Normally for ideally it should be VDD by 2. Okay, so this is called as VTH, or it is also called as VM, trip point, VTH or VM. Okay, so this is equal to VTH. So this point over here is called as the trip point, or it is also called as the switching threshold, or it is also equal to VM. So write down the definition over here for the trip point. The point at which, let's write it down over here. The point at which V out is equal to V in is the trip point or switching threshold of CMOS inverter. Okay, alright. Now we will do the analysis of CMOS inverter in the region number C, saturation region. So can we start? Everyone ready? Hello? Y'all are ready for this? We'll actually answering the question. They can ask you this separately also. Derive the expression for switching threshold voltage for the CMOS inverter. Okay, can we start now? Yeah, so let's write the first point. We will assume both NMOS and PMOS are in saturation over here, right? This is region number C from the curve. So this is region number C actually, and we are deriving the expression for VTH voltage or VM voltage. So we are deriving the expression of the following terms, that is switching threshold or trip point in region number C. So in region number C of the graph, what do you see? Both NMOS and PMOS are in saturation. Okay, so let's write that down. In region C, we will write the second point over here. At V in, we can say at V out equal to V in equal to VTH, both NMOS and PMOS transistors, let me say PMOS and NMOS transistors, are in saturation region. Are in saturation region. Okay, and what did we say about VGSN? What about the constraints? What were the constraints? Let me write in blue color. So we will rewrite it. VGSN was equal to V in, correct? And V in is equal to VTH. Okay. VDSN was equal to V out, and that was equal to again VTH over here, because your V in is equal to VTH is equal to V out. Then VGSP is equal to V in minus VDD. It's basically V in is equal to VTH, so it's VTH minus VDD. VDSP is V out minus VDD. These were the constraints which we have written a little while earlier. So V out is VTH, so it's VTH minus VDD. So these four constraints which we have to see now: 1, 2, this 3 and 4. This will have to use it over here for the NMOS and PMOS transistor. See, wherever I use suffix n, that means it's for NMOS, VGS for the NMOS, and wherever I use it P, it is for the PMOS. Okay, so let's start over here. So we'll apply, now we say that at all times we say that applying KCL, we can say that IDP is equal to, or IDN is equal to IDP. Correct? So let me write over here. Okay, let me connect my writing pad properly. Okay, so IDN in saturation, the current equation in saturation is equal to IDP. Mod of we have to write basically, but it's fine. It's fine. We can write it like that. And also we'll assume one more thing, that the channel and modulation parameter for the NMOS and PMOS is 0. So lambda n and lambda p is equal to 0. So remember, in the saturation current we have 1 plus lambda VDS term, that will not come over here. Okay, so what I mean is, see this, in ID sat equation, when we write Kn by 2 VGS minus VTO the whole square 1 plus lambda VDS. So basically what I am saying is now that this term won't come. So we only have Kn by 2 VGS minus VTO the whole square. Only this much formula will come. Alright. So now let's go ahead. Let me go to the next point. Now let's write this equation for ID drain current in saturation for NMOS. Its formula is Kn by 2, okay, VGS n minus VTO. So threshold voltage of both NMOS and PMOS will be VTN and VTOP. Remember that, because we are assuming threshold the channel modulation parameter is 0, and there is no substrate, source to substrate is 0 voltage, so there is no substrate effect. So what I am saying is VSB 0 for both the cases. Okay, so this is Kn by 2 VGS n minus VTO n the whole square, that is equal to, now I am not writing this, this is Kp by 2 VGSP minus VTOP the whole square. Okay, alright. Now we take, or we consider this ratio. There is one ratio, so what we do is, this 2 and 2 will get cancelled obviously. Let me go over here. So this 2 and 2 will get cancelled. We'll write in the next step Kn by Kp times, okay, Kn by Kp, we write it like this. So what is Kn by Kp? Yeah, we assume that Kn by Kp is equal to Kr. This is called as inverter ratio. Inverter ratio. I'll write about it in detail later, but let's use this and write step number 5. So if we say Kn by Kp is Kr, so it will be Kr times, what is VGSN? First let me write it like this only, VGSN minus VTON the whole square, and here we'll have VGSP minus VTOP the whole square. Okay, so then we'll write, then we open the bracket over here, so it will be Kr into, what is VGSN? VTH, yes or no? So this we can write it as, or basically this is VTH minus VTON square, and what is VGSP? VGSP is VTH minus VDD. This is VTH minus VDD minus VTOP the whole square. Okay, Now we have to take this square and square term, so square root out. So it will be square root of kr. Okay, so that term will be over here VTH minus VTON is equal to VTH minus VDD minus VTOP. But here you will come plus and minus term. Plus and minus term will come. I hope you are following this. Alright? Plus or minus term will come over here. So now, which term to consider? Because we are doing square root, right? Taking square root on both the sides. So here it is taking square root on both sides. Now, which term, which to consider, minus or plus? So basically, if you see carefully, this term um, is a positive term. Okay, so basically VTH minus VTON. So let's say VTH, let's take some numbers. It's around 2.5, let's say volt, and VTON is, let's say, 1 volt. So this is 1.5. This is a positive number. What about this? VTH minus VDD minus VTOP. Okay, VTH is 2.5, VDD is 5, and this is minus, so this becomes plus 1. So how much is this? This becomes minus, right? Minus 2.5 plus 1 minus 1.5. So this is basically a negative number, and this is a positive number. So what will come in the next step, number 8? What sign we should consider? Minus or plus? We should consider square root of kr VTH minus VTON is equal to minus of, not plus, only minus of VTH minus VDD minus VTOP. That is what we will consider. Okay, so in step number 9 we'll take this root of kr, and VTH will come in this side. It will become plus VTH, so it will become root kr VTH plus VTH, and I'll push this root kr minus VTN over here, so this will become plus. Yes or no? So here if I open the bracket, I'll get VDD plus VTOP. Now this minus VTON into root kr will become plus over here, so you'll get plus root kr VTON. I hope you have followed this. Now I'll take VTH common over here, step number 10. So what I will get? VTH into 1 plus root of kr is equal to VDD plus VTOP plus square root of kr VTON. Okay. Finally, my VTH term will be given by VDD plus VTOP plus square root of kr, which is the inverter ratio, into VTON divided by 1 plus square root of kr. So this becomes my equation for my switching threshold of my trip point of the CMOS inverter. So very important derivation. Okay, so this is called as switching, is almost used in all the numerical, switching threshold of threshold voltage, switching threshold voltage of CMOS inverter. Okay, now this you can write it in different form also. So how is the different form written? Let me write it that form also, form number 12. So we can write the same thing as follows: VTH is equal to, we can take divide by both the sides, I mean numerator and denominator, by kr. So what will come over here? VTON plus VDD. Okay, let me add it over here. 1 by kr times VDD plus VTOP. Alternate form sometimes useful. 1 plus square root of 1 by kr. Okay, this alternate form sometimes useful. Okay, this is the same thing only. Let's call this equation number 1.1, this as 1.2. Okay, now also one more term is also very very important. Let me add highlight this point. So if you go back to this equation, where will I happen to, yeah, step number 6, step number 6 equation. Let me rewrite that equation again. Step number 6 equation rewrite. So I'll write point number 13. Let us rewrite step 6 equation again. So what was step 6 equation again? Let us rewrite that. Kr was equal to Vth square minus Vt1 square. Let me write that. Kr into Vth minus Vton square was equal to Vth minus Vdd minus Vtop square. So what we are doing now, we are solving for Kr. Okay, solving for Kr. So now Kr will be equal to Vdd. Oh, sorry, not this. Not the step number 6. Basically, I have to cancel this. We have to go for step number 8. Sorry, step number 8. Step number 8 it is. Let me cross check. Yeah, mostly yes. Step number 8 it is. So solving for step, let's rewrite step number 8. So what is that? Root of Kr Vth minus Vton is equal to minus of Vth minus Vdd minus Vtop. This step, right? Yeah, this is it. So that is what we will write now. So let's modify this further. So it is square root of Kr Vth minus Vton is equal to Vdd plus Vtop minus Vth. Okay, now squaring both the sides, we get squaring both sides, we get Kr into Vth minus Vton square, and here we get Vdd plus Vtop minus Vth square. So what will be Kr now? Kr will be equal to Vdd plus Vtop minus Vm divided by Vth minus Vton the whole square. So that is my expression for Kr. Okay, this is also very important. Sometimes we have to find out the inverter ratio, and during those times this formula will come in handy. So please note it down. Whatever I'm putting inside the box, please note it down. Okay, this is the formula for the inverter ratio. Now for an ideal inverter, what should be the value of Kr? What should be the value of Kr for an ideal inverter? Vth, what should be the value of Vth? Vdd by 2. Yes or no? For ideal CMOS inverter. So let's find out. Derivation is over, but we are finding something else now. So this point number is 13 or 14. So now we see for ideal CMOS inverter, what we can write? Vth is equal to half of Vdd or 0.5 of Vdd. So let's find out the inverter ratio for ideal inverter. So Kr ideal will be given by, here in this equation only we'll substitute, yeah, so here Vdd minus, oh sorry, what is this Vm? This should be VTH. This should be, y'all didn't remind me, this is VTH term. Okay, yeah, this is VTH. Anyways, y'all are there in the meeting. Y'all are okay. I hope y'all are listening. Yeah. So VDD minus VTH, that means VDD minus 0.5 VDD. That will be 0.5 VDD, right? Plus VTOP divided by VTH is 0.5 VDD. So 0.5 VDD minus VTON, the whole square. Now, if we want to find KR for a symmetric CMOS inverter, we'll write for a symmetric CMOS inverter. What do you mean by symmetric CMOS inverter? Their threshold voltages are same in magnitude. That means VTO uh, is equal to VTON is equal to minus of VTOP. Okay, magnitude wise all are same. So what will be the formula for KR for a symmetric inverter, ideal symmetric inverter? So here you substitute 0.55 plus VTOP, and here you can substitute instead of minus VTOP plus VTO again P. So this factor becomes equal to 1. So KR inverter ratio for a symmetric inverter is 1. That's also a very important point. The inverter ratio is 1 for a symmetric CMOS style. Okay, this is one important observation. I hope you are listening. Can you give me a heads up? You all are there? Hello. Yeah, we have divided into two lectures. So first lecture is getting over. In the next lecture, we'll derive, I mean today only, 7 to 8. We have derived expression for VTH. Actually, we started with this. We have plotted the drain current, the combined currents, and the output voltages and input voltages for the CMOS inverter. Okay, and then we have derived the switching threshold for the CMOS inverter, which is this expression number 1.1 and 1.2. Then we have seen the expression for KR. Let me call this as 1.3. And then we have derived that for a symmetric CMOS inverter, the inverter ratio should be 1. Alright. So these are a few observations which we are finding out. Now please continue to pay attention. We'll continue this further. So next point is, what is KR? KR was actually Kn divided by Kp. Now what was Kn? Kn is basically given by Kn dash W by L of NMOS, Kp dash W by L ratio for PMOS. But what is Kn dash? Mu N Cox W by L for NMOS, mu P Cox W by L of PMOS. Okay, what is mu P and mu N? Mobility. Okay, mu N and mu P is mobility of electrons and holes. Now, what is Cox given by? Epsilon Ox upon Tox. So Tox of both the NMOS and PMOS will be similar. So we can cancel out Cox term from here. And also the technology, when we say W by L, L is the technological length, and this is normally 2 lambda. So let's say if we are using 45 nanometer or let's say 180 nanometer technology, 180 nanometer technology. So what is lambda here? 90. So lambda is 90 nanometers. So L will be 180 nanometer technology. Alright. Are you understanding? So lambda is 90, L is same. So normally L is same for both NMOS and PMOS. So anyways, this gets cancelled out and we get mu n W by L of n mu p W by L of p. Okay. Um, so kr, I mean, we can write it like this: W by L of n divided by W by L of p is actually equal to kr times mu p upon mu n. Yes? Yes or no? So normally if we consider for a symmetric CMOS inverter kr is equal to 1, then what can we write over here? Next step, if kr is 1, 60, 17 step, we can say W by L of NMOS upon W by L of PMOS is just the ratio of their mobility of electrons and holes. Yes or no? And typically the mobility of holes divided by mobility of electrons, mobility of holes is around 230 centimeter square per volt second upon mobility of electrons for silicon is 580 centimeter square per volt second. So if I divide this ratio, this will be 1 upon 2.5. I mean, okay. So we can say over here that next step will be, if I consider this mobility, this one, okay, 1 upon 1 2.5, then what can I say? W by L of of PMOS transistor is almost 2.5 times W by L of NMOS transistors. And what I've said, basically L is constant, L is technological constant, so it's basically WP upon L is equal to 2.5 times Wn upon L. L is a technological constant and it will be remaining constant, so we'll cancel out from here because it will be same. L is same for both NMOS and PMOS. So what we normally do is we keep the width of the PMOS transistor around 2 to 2.5 times the width of the NMOS transistor. W is the width of PMOS. This is width of NMOS transistor, and L is, I hope you know, channel length of NMOS and PMOS transistors. Alright? Hello? Are you able to follow this? Yes or no? So I'll end the recording of the first session now. So we call this as 44 A part. Now B part I'll record from now on. Okay, so in this lecture we have covered the CMOS inverter or the VTC curve with different operating regions A, B, C, D, E. Then we have superimposed the characteristics of drain current for NMOS and PMOS together versus Vout and Vin together. I mean VDS and VGS. Then we have derived the expression for switching threshold for the CMOS inverter. Now this is important for the sake of the derivations. This is the first derivation for the switching threshold. Then we have derived the ideal inverter. This is the inverter ratio. Kr is called as the inverter ratio. Let me write it here. This Kr is the inverter ratio. Then we have derived the condition for ideal CMOS inverter and symmetric. So for that Kr is equal to 1. And if we see Kr equal to 1, this is an important discussion going on. Cox is same for both the sides. And it seems that the mobility of holes is less than mobility of electrons. So keeping the technological length L constant for both the NMOS and PMOS, we have to, if we want Kr equal to 1, inverter ratio 1 and symmetric CMOS inverter, we should keep the width of PMOS transistor around double the width of, or almost 2.5 the width of NMOS transistors. Okay, so from here on, next we will derive the noise margins levels for the CMOS inverter, that is derivation for VOH, VOL, VIH and VIL in the next class, that is today only. Okay, So let me end the recording.